These 4 wires are made of the same metal. Rank in order from largest to smallest the electron currents from wires A through wire D. Now first let's remember what electron current is defined as. Electron current is defined as, and we've shown it to be equal to, the number density of electrons times the cross-sectional area through which those electrons move past a point, times the drift velocity of the electrons in a material. Now remember, number density, N sub E, is a property of the material. So since all of these wires are made out of the same material, they each have the same number density. So those quantities will be all the same for each one. Now what's different for some of the wires is the cross-sectional area and the drift speed. Now we see from our formula for electron current that electron current is directly proportional to cross-sectional area, and it's also directly proportional to drift speed. So this means the larger the cross-sectional area, the greater the electron current. And that's because the larger the cross-sectional area, there are more electrons that are able to move, more electrons present. And also the faster the drift speed of the electrons, the greater the electron current, because you're getting more electrons crossing that cross-sectional area per unit time. So our task then should be to compare the things that are different. Let's compare the cross-sectional area of each of these wires and the drift speed, and let's compare it in such a way so we could see quite easily which wires will have the greatest electron currents. Let's start with wire A. So wire A has an electron current that's given by the current density, which I'll just use N sub E for all of them, since we know that they all have the same number density of electrons being made out of the same material. Now wire A has a cross-sectional area equal to pi times the radius squared, and it has a drift speed v. So let's use wire A as our standard of comparison. We'll compare each of the other wires to wire A. So let's look at wire B. Notice that wire B, for example, has the same cross-sectional area as wire A. Also notice that for wire B has twice the drift speed as wire A. This means that the electron current for wire B, if we did our math right, and the math on this is very simple, is equal to twice the electron current for wire A. And in this situation, it's twice the electron current of wire A because the electrons in wire B move with twice the drift speed as wire A, even though the cross-sectional area is the same. Now let's look at wire C. First thing I notice about wire C is it has twice the radius as wire A. Twice the radius of wire A means it's going to have 4 times the area, as we'll see here. So the area is pi times the radius of wire C squared, which is equal to pi times 2 times the radius of wire A quantity squared, which is 4 pi the radius of wire A quantity squared. So what this says is wire C has 4 times the cross-sectional area of wire A. Now the drift speed of the electrons in wire C is the same as the drift speed of the electrons in wire A. So what this means is that the electron current for wire C is equal to the number density times 4 times the cross-sectional area of wire A times the drift speed. So we could say that the electron current for wire C is 4 times the electron current for wire A. Now that makes sense, because if it's moving at the same speed as the electrons in wire A, and if the wire C has 4 times the area, then that's going to be many more particles that are able to even cross that point in the same amount of time. Now let's look at wire D. Thing to note on wire D is it has only 1/2 the radius of wire A. 1/2 the radius means that wire D is going to have 1/4 the cross-sectional area of wire A. So what this tells me right away is, since it has 1/4 the cross-sectional area of wire A, there's fewer electrons that we have to work with. But in this problem, we see that wire D's electrons move with twice the drift speed of wire A's electrons. So let's see what this means for the electron current for wire D. Wire D has the same number density of electrons as each of the other wires, being made out of the same material. It has 1/4 the cross-sectional area of wire A, and the electrons in wire D is moving with twice the drift speed of the electrons in wire A. This ends up being equal to 1/2 the electron current of wire A. So now that we have the electron currents of each of the wires expressed in terms of the electron current of wire A, we can compare them. We see that wire C has 4 times the electron current as wire A. We see that wire B has twice the electron current as wire A. And we see that wire A has twice the electron current as wire D. So we have now ranked the electron currents from largest to smallest. And notice the electron current depends not only on the properties of the material, not only on the fact that it's a particular metal, but on the cross-sectional area through which those electrons are moving and the drift speed. And drift speed is a property of the metal.